Hello everyone, welcome to the fourth lecture of the second module where we are discussing different characteristics of sensors. In previous class, we have discussed thermal noise, or sometimes we also call it Johnson noise or Johnson-Nyquist noise, right? So for that, what we have done is we have taken an amplifier and we have seen that we had an input signal without any noise. However, at the output, we had a output plus some noise, right? Now, this source of noise was not known, okay? By some interpretation, we have reached to a point where we have concluded that the source of this noise is actually internally generated in the components of this amplifier, okay? These components include some active and passive components, which can be resistors, capacitors, inductors, or some active components like transistors. Now, let us see short noise. Short noise is very specific to semiconductor materials, and in the microsensors, we use these semiconductor materials, say for a chemical sensor, as a channel material or as a receptor material, okay? So, the internally generated noise in semiconductor and vacuum tube devices on account of random movement of charges is called short noise, okay? The random fluctuation are caused by the carrier's random arrival time, which produces a short noise, okay? So we know that in a semiconductor, mostly you have carriers in the form of electron and holes. You may have some ionized ions as well. They all have different masses and they may possess different energy. That's why nature of vibration is different if you take them separately, okay? Of course, you can study their vibration collectively, okay? And this random fluctuation happens because of this difference, okay? And this is produced as short noise, okay? These signals, as I was mentioning, is mostly carried by electron, holes, photons, as well as phonons, okay? So you can understand the short noise as a random and quantized event, okay? Because I have quantized it with random arrival time, okay? Short noise depends on the transfer of the individual electron across the junction, if you talk about junction devices, okay? If your bandwidth is say delta f, and if I is the average current passing through this junction that I am talking about, okay, and if E is the charge of electron, I can say that the short noise is root 2I E delta f, okay. So the short noise is dependent on the bandwidth also. So similarly, for thermal noise also we have seen that it has great dependency on the bandwidth, okay. So how to reduce this short noise, okay, because this is biggest problem and it will always exist because this random fluctuation will always be there in the arrival time of the carriers, okay. So not much can be done to reduce the internally generated noise in semiconductor devices, as the noise is on the account of acceleration of charges, okay. You stop acceleration of the charges, you can avoid short noise, but can the acceleration be avoided? No, because all these junction based devices work on some potential difference. Say if you talk about say a diode, okay, if you talk about a diode, say if I have a PN junction, we know that it work in forward and reverse bias condition, but in both the cases you have provided some potential difference, okay, and when you are providing some potential difference means you are accelerating the charges, right. So it means that short noise cannot be removed completely, however you can reduce it, okay. So usually different filtering techniques has been proposed to reduce the short noise. Therefore, we can say that selective filtering can be helpful in removing or at least reducing this short noise in junction devices. Okay. Now, there is one more noise which is associated with the receptor material of a microsensor, which is generation recombination noise. We call it GR noise. Okay. This noise is produced from the generation and recombination of electron and holes in a semiconductor. Okay. So, you know that this generation and recombination can be because of various reasons in a semiconductor. Okay. And again, they are also observed in junction based electronic devices. Nearly all the electronic devices have junctions, right? So, this is also localized to this junction based devices. Okay. Then another noise which is very important to be understood is pink noise. Okay. In this noise, the component of the frequency spectrum of the interfering signal, okay, are inversely proportional to the frequency. Okay, and usually this pink noise is more prominent at a lower frequency as compared to the higher frequency side. Okay, and each octave carries an equal amount of noise power. Okay, in this case of pink noise. Okay, although the origin of pink noise is not understood completely, however, there are efforts which are in place to reduce this pink noise. Okay, these were all discussions on internally generated noise. However, let's come back to the original example that we have taken. Example of an amplifier, okay, and signal, input signal, okay, and the output was output plus some noise was there, and of course this is used to amplify some signal from a sensor. So this is your sensor, right? Now we have discussed till now the internally generated noise. Okay. However, we have discussed that there are some other noises also, like conducted noise and radiative noise. Okay. Let us see what is conducted noise. Okay. Particularly in the context of this kind of setup. Okay. The power supply to the amplifier could be the source of noise. Okay. You know that all this amplifier works on some DC biasing, right? So it can also be a source of noise, the biasing itself. Okay, since it may have spikes, ripples, or random deviation from the origin that are conducted to the amplifier circuit through the power wiring. Okay, and since this noise is being conducted through different wires and all, it is known as conductive noise. Okay. So conducted noise can again be minimized by using a very stable power system and other taking other precautions. Okay. However, it become more prominent if you don't take these things into consideration. Okay. Then next thing is the radiated noise. Let's take the same example: a sensor, amplifier, and a signal to be amplified. Okay, which is of course coming from this sensor. Okay, you have a amplifier and you have a signal plus the noise. Okay, so internally generated noise we have seen. Conducted noise, I am telling you that it is coming from the say power supply which is used for biasing and other purposes for this amplifier, right? Then let's understand the radiated noise. Okay, there may be electric or magnetic disturbances in the ambient around the amplifier. Okay, because of which unwanted signals are radiated into the interior of the amplifier. Okay, and it contribute to the overall noise. Okay, and this noise is known as radiated noise. Okay, say you are doing this measurement in a lab where your another friend is using some say instrument which is generating a lot of vibration, or which can generate say magnetic field. Okay, some magnetic flux of lines are coming, okay, and interfering with the currents here. Okay, right? So if your sensor is carrying some conductor, okay, it may also induce some eddy currents. Okay, and it may altogether be a different a noise structure and it can be never be predicted. right? So therefore, radiated noise can be minimized by working in isolation. Like if the whole system has some, say, EMI or EMC shielding, okay, or you do other provisions to minimize this radiative noise to the amplifier or the sensor. Okay, so these are all about different noises in microsensors and nanosensors. Okay, we have seen all this noise in very brief. Okay, all right. So we have understood the various noise that exist in a sensing system. Okay, now let us see that even if we have some some noise, then also we have some, say, signal to noise ratio which is much higher than noise, right? So how erroneous my signal is. Okay, so the sensors comes with some error percentage. Okay, the results are determined in or represented in some percentage error. So let's see the errors associated with these sensors. They are very crucial, particularly for representing the data of the sensor. Okay, and it's become more critical when you are talking about end user who has nothing to do with the manufacturing or fabrication of these sensors, right? So the important error, one of the important error is limiting error in this case of in this case. Okay, so the sensor manufacturer has to specify the deviation from the nominal value of a particular quantity. Okay, the limit of this deviation from the specified values are defined as limiting error. Okay, we'll understand this concept with some example. Okay, now let us consider that the magnitude of quantity having a nominal value, say AS, representing with the AS subscript as shown over here, and having a limiting error of plus minus delta A. Okay, now this sensor should have a magnitude, say AS subscript A, which is in between AS minus delta A and AS plus delta A, right? Let's understand this in little more detail. Okay, now I have a sensor, again a chemiresistive sensor, as we are taking example. Okay, we have a chemiresistive device. Okay, and the output of the sensor is in some, say, resistance value or say current value. Okay, now say the manufacturer has given the nominal value of the sensor to be, say, 70 nanoamp. Okay, and have a limiting error of, say, plus minus 5 milliamp or say plus minus 10 milliamp. Okay, now the manufacturer, and of course this is a gas sensor, so he has given this change value of the current, say for a particular concentration of gas, say 70 ppm of some gas, say hydrogen sulfide. Okay, so for 70 ppm of hydrogen sulfide gas, there is a current change of 70 nanoamp. Okay, with a limiting error of plus minus 10 milliamp. Okay, now it means that the manufacturer is guaranteeing this current value to be in between, say, 60 to 80. Okay, so he is saying that, okay, you may not get the exact value of 70. Okay, but the sensor may represent some data between 60 to 80, and you should understand that it's a 70 ppm S2S. Okay, so that is the importance of nominal value and the limiting error. Let's see this relative error in a little more detail and some more variation in this relative error. Okay, the relative error is defined as the ratio of the error to the specified magnitude of a quantity. Okay, or mathematically, relative error is the actual value minus nominal value divided by nominal value. All right. So as from the previous example, if I want to calculate the relative error, and for the same case of the sensor where for certain concentration of H2S, my actual value is 70 nanoamp. Okay, or say actual value is not coming 70 nanoamp, but it is coming something like say 75 nanoamp, okay, minus the nominal value. We have taken 70 nanoamp as nominal value. So 75 nanoamp minus 70 nanoamp divided by 70 nanoamp, right? Relative error is actual value minus nominal value divided by nominal value, okay. So that is how you should calculate the relative error. Now let us see, when you add two quantity or you subtract two quantity, or if you do multiplication, okay, or you divide, how this relative error propagates, okay. And that is very important, particularly for the concept of say sensor array, okay, when you have multiple sensors working together, okay. Usually, say for example, if I want to, I am giving you one example of sensor array in case of say multi-gas detection system, okay, or you might have heard e-nose, okay, electronic nose, okay. So just I have given you one example of hydrogen sulfide sensor, okay. If I am having a e-node system, this H2S sensor will be part of it. There might be a number of sensors working together, okay. Sensor 1, say S1, 2, 3, 4, 5, 6, okay. 5 or 6 data are being acquired together, okay. For those complicated cases, you should understand how this relative error propagates, okay. Let us see with some simple example of when you are adding two quantities, okay. Let's see how it propagates, okay. So you say you have a two quantity x1 and x2, okay, and say x1 and x2, and capital X is the final result after adding this x1 and x2, okay. Now let us see what will happen if you consider the relative changes in x1 and x2, how it is going to affect capital X, okay. So the relative increment of the function, this function can be given by simple differentiation of x with respect to x, capital X, okay. So I can write dx by x. If I want to find this relative change, I can write this dx by x equal to d by x of x1 plus x2, right? Or it is the dx1 by x plus dx2 by x, right? This dx by x is equal to dx1 by x plus dx2 by x, right? Now what it denotes, dx1 by capital X will not signify anything for us, okay, because I want to see change in x1 with respect to itself only, not with respect to capital X, okay. So what we can do is, we can multiply numerator and denominator with x1, okay. So I can write this term as dx by x equal to x1 by x1 into dx1 by x, okay. Similarly, you can write for the second term, all right. If I will rearrange it, I can write dx by x equal to x1 by x dx1 by x1 plus the second term, which is similarly for x2, x2 by x into dx2 by x2, okay, and this is your final result, okay. So if you want to find the relative errors, what you have to do is, you have to multiply each component with their own value divided by the summation of that, means capital X is x1 plus x2. So I can also write this like dx by x equal to x1 by x1 plus x2 into dx1 by x1 plus x2 by x1 plus x2 into dx2 by x2. Okay, this is how relative error propagates when you add multiple terms. Similarly, you can write for three quantities. Okay, so if the limiting errors in the component are represented by plus minus delta x1 and plus minus delta x2, then the corresponding relative limiting error in x can be given as plus minus of this value, or delta x by x is equal to plus minus x1 by x1 plus x2 into del x1 by x1 plus x2 by x1 plus x2 into del x2 by x2. Okay, so this equation shows that the resultant limiting relative error is equal to sum of the products formed by multiplying the individual relative limiting errors by the ratio of each term to the function. Okay, so individual relative limiting errors are del x1 by x1, and for x2 it is del x2 by x2. Okay, you are multiplying it with the ratio of each term with its function x1 divided by capital X, which is x1 plus x2. Okay, and similarly you can write for multiple terms. Okay, so then difference of the two quantities. Let's see for x1 and x2 when they are subtracted. Now you have a function of x equal to x1 minus x2. Okay, so del x by x, okay, del x by x can be written as del x1 by x minus del x2 by x. In one go, we think that it should be very similar to the summation, but it is not. Okay, let us see this case. Okay, now let's express this result in terms of the relative increment of component quantities that we have for the addition. Okay, I can write it as dx by x equal to x1 by x into dx1 by x1 minus x2 by x into dx2 by x2. Right? Now, if the errors in x2 and x1 are, say, plus minus del x2 and plus minus del x1, okay, the signs may be interpreted to give worst possible discrepancy. When the error in x1 is plus del x1, the error in x2 should be minus del x2, and vice versa. Then only I will have maximum error. Okay, then the relative limiting errors in x can be written as, del x by x equal to plus minus x1 by x into del x1 by x1 plus x2 by x into del x2 by x2. Okay, this we have got when I am taking the error in x1 as plus del x1 and error in x2 I am taking as minus del x2. Okay, see this condition. Okay, you are taking this as minus del x2, that's why the overall terminology is going to be plus. Okay, and this gives you the maximum error condition. Okay, or as I have mentioned, the worst case. Okay, these values will again depend on various other factors that we are going to discuss in our next module. Okay, which will be very localized to the transducer that we are using in the device. Okay, similarly, the relative error calculations can be done for product of two quantities, product of say x1 and x2. Okay, say a function x is written as x1 into x2. Okay, to find the condition of relative limiting error, we take log on both sides. So if I take the natural log on both sides, I have log x equal to log x1 plus log x2. Let's differentiate the above equation with respect to x. Okay, and if we do that, we get a value of 1 by x is equal to 1 by x1 into dx1 by dx plus 1 by x2 into dx2 by dx. Right? what I have done is I have differentiated the equation. Okay. Now I have 1 by x is equal to 1 by x1 into dx1 by dx plus 1 by x2 into dx2 by dx. Okay. What I can do is I can bring this dx to this side, right? So my equation will be dx by x equal to dx1 by x plus dx2 by x2. Okay. Now for the relative limiting error in x, I can write that del x by x is equal to plus minus this value del x1 by x1 plus del x2 by x2. Okay. So what we understand from this particular equation, the relative limiting error in a function which is multiplication of two quantities is equal to summation of the relative limiting error in the two quantity. Okay. Delta x1 by x1 plus delta x2 by x2. However, when we have done addition of the quantities, addition of x1 and x2, the function x was x1 plus x2, we were getting this term delta x1 by x1, okay, multiplied with the nominal value or the value of the quantity divided by the function itself. Okay. So that is the difference when you add two quantity and you do multiplication of this two quantity. Okay. When you add it, the relative limiting errors do not get added. Okay. They come with some another factor, which is the quantity itself divided by the total function. I hope it is clear to you. Okay. When you are doing multiplication, what you are getting is del x by x is equal to summation of individual relative limiting errors. Okay. Del x1 by x1 plus del x2 by x2 and so on. Okay. Now let us see the same thing in case of product of two quantity. Okay. Now let us see the same thing for division. Okay. X is equal to x1 by x2. The function is x, which is x1 by x2. Same thing, same process we will do. We'll take log on both sides. Okay. We'll have log x is equal to log x1 minus log x2. Okay. Now let us differentiate this particular equation. Okay. If I differentiate this equation with respect to x, okay, I will get 1 by x is equal to 1 by x1 into dx1 by dx minus 1 by x2 into dx2 by dx. Okay. Again, I can take dx to other side and I will have the equation as dx by x is equal to dx1 by x1 minus dx2 by x2. Now, relative limiting error in x can again be calculated by taking the worst condition. Worst condition means when you are taking what we have seen in case of subtraction. Okay. When the error in x1 is plus delta x1, the error in x2 is minus del x2. Okay. The similar condition if you take here, okay, the relative limiting error in x will be del x by x is equal to plus minus del x1 by x1 plus del x2 by x2. Okay. So we have seen addition, subtraction, product of two quantities and their propagation of the relative error or relative limiting error, and then we have seen for division. Okay. Let us see for a power of a factor. Okay. Now say x is a function of x1 where x1 where x is equal to x1 to the power n. Okay. Now we'll do the same process. We'll take log on both sides. We have log x is equal to n into log x1. Okay. Let's differentiate this expression with respect to x. We have 1 by x is equal to n by x1 into dx1 by dx. Alright. So we can write dx by x is equal to n into del x1 by x1. Okay. So if I have to write relative limiting error in x, I can write as del x by x is equal to plus minus n into del x1 by x1, where n was the power of the quantity, okay, where x1 was the quantity and x was the function of x1. Okay. So if I have to find the relative limiting error in x for a function x1 to the power n, what I will do is I will simply multiply its power to the relative limiting error in the quantity itself. Okay. So I hope that with this the concept of relative limiting error is clear to you. Okay. We'll discuss some more kind of errors in our next class. Thank you.